It's my pleasure to provide updates on the GA4GH Infrastructure Challenge and the Multiple Myeloma Challenge. But first, I want to give some fodder to the discussion that's going to happen after this when we talk about the good, bad, and the ugly. And that's to touch on this new paradigm that we've been exploring for hosting data challenges, and that's the submission of models and not predictions. And that's happened in a number of challenges now, and I think despite some hiccups, for the most part successfully. For those who haven't been part of these challenges where you've been submitting containerized models, this is pretty much the structure. So challenge teams are formed, and most often they have access to training data sets for which they can develop models. These models are then containerized. Docker is the most popular form of this containerization, and then these models are sent to the challenge organizers. And so the double line in the middle represents a firewall where there's no kind of information that can leak out. And this gives the organizers a lot of flexibility in terms of being able to run these models on data sets that are inaccessible to the participants. And importantly, it allows us to run on new data or prospective data. And it allows us to then score these over time, create leaderboards and benchmarks. And I think this is a really kind of important paradigm in how we scale what we do and how we improve reproducibility and how we have a more robust framework. Of course, there's pros and cons, which I'll just enumerate here. So the pros, I think we all understand, is reproducibility, the ability to run and rerun models independent of the modeler themselves, the use of newer prospectively collected data, and importantly, the use of private or sensitive data, such as personal health information. So some data is just never going to see the light of day because of its sensitive nature, and so this allows this data to be used in a way that it wouldn't be otherwise allowed. Of course, the cons, as many of you experienced, this is more upfront work for you. You have to make your model robust to unseen data, whether it's, there's missing data or distributions that might be unexpected. So these are things that are a challenge for you in terms of how you kind of bulletproof your models before sending them to us. Another difficulty is how do you troubleshoot models that go awry? So you don't necessarily see the errors or the problems that arise when we run these models. This is obviously something that we have to improve, as well as confusion about the compute resources. So you need to know how much memory or how much CPUs or things of that sort. So these are things that are addressable. So it's important to know that this will be the future of Dream. We will continue to use Docker and cloud platforms, and I think more and more you'll see this integrated into challenges. So first of all, thank you for your patience, because this has been a learning experience for us as we've introduced these systems and tried to develop infrastructure that streamlines this process. So we're obviously interested in your feedback and would like to know how to improve. And we will be making improvements in terms of how we streamline this technology. So we'll be adding more test queues so you can submit your models and have them validated and operating on simulated data or kind of dummy data sets. We need to provide richer descriptions of the data and more information about the hardware and resources. So, so that's all I wanted to say about this Docker and the cloud platforms that we've been operating these on. And this is a good segue to the G4GH Dream Infrastructure Challenge. This is a very different challenge. It's not your typical challenge. So this is in partnership with the Global Alliance for Genomics Health. And the intention for this is to really develop a community effort to evaluate, benchmark, and develop tools and platforms for reproducible, portable, and scalable pipelines. So this kind of course, feeds into what I was just saying, how we need to improve our infrastructure to running these models. And this is really a series of challenges focused on community standards, such as Common Workflow Language and the WDL, which is a Workflow Definition Language, as well as some of the G4GH APIs. So who's participating? Well, not your typical modeler. These are more for platform developers who can assess and improve the compatibility and performance of their different platforms and to help and resolve issues with standards and APIs, as well as the platform users. Many of you are platform users who could provide feedback to developers. And really anyone who's interested in building and using reproducible pipelines. So the structure of this is we provide workflows that are a combination of Docker files and shell scripts and R tools, as well as WDL or CWL descriptor files, which kind of bind everything together. So we provide these workflows, which people will then download. We give the input files into these workflows, and we expect a set of output files that should match what should be expected. So this is essentially how we run this challenge. We have a number of different contributed workflows. We started very simply with just a hello world. Right? You should be able to run that and get it to print hello world. And then we progressively moved into harder and harder workflows, beginning with an MD5 sum, and then moving into real bioinformatic workflows, including ChIP-seq workflows, the GDC DNA-seq workflow, ENCODE, and others. And this is a growing set of workflows that will be accumulating over time. So not only is this a rich resource for you to have access to these workflows and pipelines, but an assessment of how well they can run in different environments. So this is a very simple challenge. One goes to Synapse, one downloads the workflow folder and all the contents. You run the workflow. You upload the results, the output, to us, which we validate. We have an automated validation script. And then you have to, of course, document the platform and environment that you're running in, because that's, of course, what we're truly interested in, is how does this workflow operate in different environments. And that's depicted here in terms of the very rich and complex universe that we're now operating in, where you have CWL or WDL, and many of the different workflow systems and compute environments that includes Galaxy and Toil, Nextflow, Seven Bridges, Curoverse, Firecloud. I mean, there's an increasing proliferation of these. And many of you have to figure out how do you run and operate these workflows in different environments. And so we're trying to help streamline this process of evaluating how these workflows run in different environments. So here's our leaderboard. You know, of course, everyone's a winner in this challenge, so long as your output matches what we expect. So what we're really trying to measure here is diversity. So multiple combinations of different workflows, different platforms, and combinations of these. And so we really appreciate many of the groups who have been participating in this, and this will be, as I said, an ongoing exercise. Okay, so let me run into the Multiple Myeloma Dream Challenge. So the point of the Multiple Myeloma Dream Challenge was to improve the identification of patients who are at high risk. Fortunately for multiple myeloma patients, they've seen a progressive increase of overall survival over the years, measured by the survival curves that are moving increasingly to the right over time. But there remains a set of patients who are truly high risk. 20% of patients continue to have a poor outcome with less than 3 years of overall survival, despite optimal care. So the interest is being able to identify these high-risk patients up front. We're talking about newly diagnosed multiple myeloma patients, and get them better treatments that might improve their overall survival. Now, there's really no consensus on high-risk markers. Of course, age is a factor, as well as clinical stage, which is the ISS criteria. But many have explored other arenas for improving or identifying risk markers, including gene expression, structural variants, copy number, and karyotypes. And so in the process of organizing this challenge, we reached out to many key data contributors and were able to obtain over 3,000 samples with curated clinical follow-up, DNA sequencing, RNA sequencing, translocation information, and that became the basis for what people would be generating their predictions from. We had a very nice turnout. We had over 483 registrants with 33 teams submitting models. And again, this was also structured with the Docker framework. People had training data made accessible to them, including the Multiple Myeloma Research Foundation generously provided their cohort for training. People submitted their Docker containers, and then we validated this on hidden data sets, including those from Dana-Farber, University of Arkansas, and Moffitt. And this is data that, again, would never have seen the light of day otherwise. So this is only made possible by the use of this Docker framework. So we had three sub-challenges. The first is based on variant calls and clinical demographic and cytogenetic data alone. The second perturbation to this was challenge 2, where you can use gene expression but not the variant calls. And finally, question 3, where you can use all three data. You can use all data available to you to generate your predictions. Submissions were scored using the integrated AUC as the primary metric and balanced accuracy as a secondary metric. And as with most challenges, we use a Bayes factor to determine statistical ties. Here's the timeline. As you can see, we're just at the end of the challenge, but not quite at the full end. So you're going to see me present some results, but not quite all of the results, and I'll explain that shortly. So here we are with challenge 1. This is, again, just using variant and clinical data. You see that the top performers is shown in yellow, and these are all statistically tied, are between an integrated AUC of 0.6 to 0.65. So not phenomenal performance, of course, better than random. But you also see age and ISS, which is the baseline metric, statistically tied with these other top models. So question 2, so what we learned from here is that there's very marginal improvement over the age and ISS model alone when you use just variant information. When you move to the second challenge, this is using gene expression, we see a better performance, where the top performers are performing between 0.65 and 0.7 integrated AUC. And what we learned here is that, of course, expression-based are better than the variant-based callers. As well, these top models are new models that exceeded the published standards. And in fact, when you look at one of the richer data sets, this is the University of Arkansas data set, you see that, in fact, some of these models are getting up into the 0.7 to 0.75 integrated AUC range, and many models are surpassing the existing benchmarks that have been published. Okay, so you notice on all my slides I didn't actually mention any team names. That's because that was going to remain private until we announce this. We have an oral presentation at the American Society of Hematology. This is on December 9th that we'll be actually announcing the teams associated with these performances and therefore who actually won these sub-challenges. Okay, so in conclusion, we were successfully utilized Docker in this context to validate in hidden data, and we observed that the multiple myeloma risk models obtained were able to outperform current benchmarks in the field. So let me just acknowledge quickly many of the data contributors, including the Multiple Myeloma Research Foundation, Dana-Farber, Moffitt, Mtugen, all the hard work from Sage. Celgene was a sponsor. And let me also thank all the participants that were part of this challenge. So thank you, and I'll take questions.